Well, we can go through this together, but first of all, can you suggest what would be a reasonable electron pushing arrow here? What would be one reasonable electron pushing arrow?
From either of the pi bonds.
There, good. Let's go ahead and draw that in. Good. Good, and we'll try to draw the products from that. Doesn't really matter which pi bond we use so far because this is a symmetrical molecule. Well, let's draw what the intermediate would look like from that step. That's good. Now there was no arrows connected to this pi bond, so we should not be adjusting it at all at this point. Why did you put the positive charge on the left-hand carbon and not this right-hand carbon?
Because it's more it's more stable with the secondary.
It's more substituted. That was fine. This is secondary, and this would be primary. So you were absolutely right to put the positive charge over here. And there's a new hidden hydrogen that I'm not going to draw over here where the hydrogen came in. Okay, well, let's just keep going. What would be a logical next step? Just following along with the same ideas that we've seen before. Good.
And I was initially gonna move the pi bond, but then that would put a positive on a first degree.
Ah, okay, so we'll talk about that in a second. That's a good instinct. Let's talk about that in a second. Well, we could stop right here. Here we have this product. So far, this is exactly the same as when we attacked normal alkenes before. It's totally reasonable for a negative charge to attack a positive. By the way, is this a stereocenter?
Yes.
Yeah, it is. So would we expect one product or two? Two. Technically, I should draw one product where this is on a wedge and one where it's on a dash. But I'm not going to bother doing that because your instructor didn't bother with that in the notes. So I'm guessing that maybe he's not really focusing on stereochemistry for this portion of the course. I can't be sure of that, though. If he had sample exams, that would be better so that we could look at the exams he's given you. But
typically, his finals are multiple choice. So
okay.
If I had the knowledge that we're going to have two products with stereocenter, then
the whole test is multiple choice? Wow, that's weird. All right, well, anyway, that'll certainly clue you in. So I won't spend much time on that because that's not in the notes. But technically, we should be drawing two products here. One where the bromine is on a wedge and one where it's on a dash because we're forming a stereocenter. And how do we know we're going to get both of them? Because we're attacking something trigonal planar. Anytime you attack something trigonal planar, you expect a maximum of two products. But I won't get into the stereochemistry here. What I think is going to be more important for your test is regiochemistry, what region the bromine will end up, not what position in space. Now, you were already having a good instinct here, which is that you were thinking about doing something else here. So far here I've just redrawn identically this picture. And you were thinking that instead of having the bromine attack at this carbon, you were thinking about moving this pi bond over here. Now, there's a couple important things to say about that. First of all, it's important to realize this is now not a reaction arrow, this is now a resonance arrow. This would be resonance. Resonance is when you're simply moving pi electrons around inside a single molecule. This is a reaction arrow because it involves two separate molecules. But if we're just moving pi electrons around inside a certain molecule, that's just resonance, which means I should now draw not a reaction arrow, but a resonance arrow. I'm going to draw a resonance arrow double-headed. And let's actually draw what the other resonance structure would be here. You were worried that that might not be stable enough, but let's draw that. You got it. Here's the other resonance structure where the positive charge is on this left-hand carbon. Now, you were worried that this is not worth drawing because we don't like forming primary carbocations. Now, that's true. However, this primary carbocation is worth drawing because it's stabilized. What's it stabilized by? By the resonance. This primary carbocation can be formed because it's being stabilized by resonance. In fact, I think we were talking about this a couple minutes ago or earlier today. we were talking about how, whereas in the past we would not have formed primary carbocations, it's okay to form what we can call here these allylic carbocations. Here we're forming an allylic primary carbocation. Well, this is being stabilized. It's being stabilized by resonance. You can see how it's being stabilized because the positive charge is really spread over the primary carbon and this secondary carbon over here. So it's okay to form primary carbocations if they're stabilized by resonance. Previously in the course we said don't draw primary carbocations, but now we have to throw that out, and now we have to say don't draw primary carbocations unless they're stabilized by resonance, but you should draw primary carbocations if they are stabilized by resonance. That's perfectly fine. Now we still have the bromine now. So what would be a reasonable reaction to have happen now? Good. Good. By the way, it's very important in these problems to make sure that you're not adding or dropping carbons.
That's exactly right.
You always want to keep counting. If necessary, put in some numbers to make sure you're not adding or dropping anything. So that would give us this product. Well, now we've said that we had our intermediate, our carbocation intermediate, had two different resonance forms. A resonance form where the positive charge was on this right-hand carbon, and a resonance form where the positive charge was on the left-hand carbon. And that means that there's two different products we can get. If basically what that means is, remember that the true molecule is a blend of these two resonance forms. The true molecule is a blend of these two resonance forms, which means that really both this carbon and this carbon have positive character. They both have carbocation character. That means sometimes the bromine will attack this carbon, and sometimes the bromine will attack this carbon, which means we're now going to get a mix of products. We're going to get both this and this. So that's the main thing to watch out for when you see this type of problem on the test. It would be so they're going to say something like draw all products or pick all the products. Well, you don't want to just draw the one product. Now you have to draw the product that we get from the original intermediate, but also we have to draw any other products we can get by drawing other resonance structures. The key thing here is to draw all the possible resonance structures and then show the bromine attacking at all possible places. By the way, is this a stereocentric?
No.
No. So here we're definitely just going to get the one product. All right, so that's the big new thing to watch out for here. If you form a carbocation intermediate from now on, you have to ask whether there's any other resonance structures of that. And if there are, you have to show the nucleophiles attacking at all the possible resonance structures. Because in general, we're going to get a mix of both products. Now, this product came about. We get this product when the hydrogen attaches here and the bromine attaches adjacent. But this is the product that we get when the hydrogen attaches here and eventually the bromine attaches all the way opposite to it. How did the bromine end up so far away from the hydrogen? Because of this resonance that we had here. So what would be good names for these two attacks? Well, this is called the 1,2 product, or 1,2 addition. This is the 1,2 product because it was the product of 1,2 addition. And this is called a 1,4 product because it's the product of 1,4 addition. Now the 1 and the 2 and the 1 and the 4 here are not IUPAC numbers. We're not saying that this would actually be the number 1 carbon, IUPAC. In fact, this would not be the number 1 carbon. The number 1 carbon would be over here on the double bond. However, they're just reference numbers. All this means is that the two attackers ended up adjacent to each other. 1 and 2, adjacent to each other. So if we thought of this as 1, this would be 2. Again, we're not thinking of these as IUPAC numbers. The only point is that they're adjacent. Whereas in 1,4 addition, the only point is if we call the place that the hydrogen ended up number 1, then where's the bromine? Well, it's not on the 2, it's not on the 3, the bromine is on the number 4. Again, we're not saying that those would actually be the IUPAC numbers, it's just indicating that the bromine and the hydrogen are on carbons that are in a relationship of 1 to 4 with each other, with 2 other carbons between them. Whereas in a 1,2 addition, there's no other carbons between them. So those are important names that are probably going to be tested. Does that make sense? let's show the mechanism and draw all products here.